Now we are starting with organic chemistry, Pradeep's Organic Chemistry, volume 2nd, whose author is Dr. S.N. Dhawan. And we are starting with the chapter whose name is alcohols. So we are starting with this chapter. This is the chapter number 1 of our organic chemistry book this year. So starting with the introduction. So alcohols may be regarded as hydroxy derivatives of aliphatic hydrocarbons. Depending upon whether the number of OH groups present in a molecule is 1, 2, 3 or many, alcohols are further classified as monohydric, dihydric, trihydric or polyhydric respectively. Ethyl alcohol is a monohydric alcohol, while ethylene glycol is a dihydric. Glycerol is a trihydric alcohol, while alditol is a polyhydric alcohol. It may be pointed here that in dihydric, trihydric, and polyhydric alcohols, each hydroxyl group is attached to a different carbon atom. This is because the presence of two or more hydroxyl groups on the same carbon atom makes the molecule unstable and hence immediately loses a molecule of water to form an aldehyde ketone or a carboxylic acid. You can see this reaction in which carbon has two hydroxyl group attached, which loses a molecule of water and make an aldehyde or a ketone. And when carbon has three hydroxy groups attached, it will lose a molecule of water and will become carboxylic acid. So alcohol containing one hydroxyl group per molecule are called monohydric alcohols. These can be divided into two broad categories: aliphatic alcohols and aromatic alcohols. Aliphatic alcohols are the alcohols in which hydroxyl group is linked to an aliphatic carbon chain are called aliphatic alcohols. For example, methanol or methyl alcohol, ethanol or ethyl alcohol, propanol or isopropyl alcohol. Second are aromatic alcohols. Aromatic alcohols in which the hydroxyl group is linked to an aliphatic carbon chain are called alcohols in which hydroxyl group is present in the side chain of an aromatic hydrocarbon are called aromatic alcohols. For example, we have three examples here. First is phenyl methanol, that is benzyl alcohol. Second one is 1-phenyl ethanol, that is alpha phenyl ethyl alcohol. And third example is 2-phenyl ethanol, that is beta phenyl ethyl alcohol. Monohydric alcohols are further classified as primary, secondary, tertiary according as the OH group is attached to primary, secondary or tertiary carbon atom respectively. For example, ethanol or ethyl alcohol is a primary alcohol, propanol or isopropyl alcohol is a secondary alcohol, 2-methylpropanetol or tertiary butyl alcohol is a tertiary alcohol. This is evident from the above structures that the characteristic or functional groups of primary, secondary and tertiary alcohols are CH2OH, CHOH and COH respectively. Monohydric alcohols have the general formula CnH2n plus 1 OH, where N is equal to 1, 2, 3, etc., or ROH, where R is an alkyl group. These are named by the following three systems. First one is the common system. In the common system, monohydric alcohols are called alkyl alcohols. Their names are derived by adding the word alcohol to the name of alkyl group present in the molecule. For example, methyl plus alcohol gives methyl alcohol. Isopropyl plus alcohol give isopropyl alcohol. Tertiary butyl plus alcohol give tertiary butyl alcohol. Second system is the carbinol system. In this system, methyl alcohol is called carbinol, while all other alcohols are named as derivatives of carbinol. For example, methyl carbinol, dimethyl carbinol, trimethyl carbinol, triphenyl carbinol. IUPAC system. In this system, alcohols are called alkenols. The name of an alcohol is derived by replacing the final E from the name of corresponding alkane by suffix -ol. The longest chain containing the OH group is selected as the parent chain and numbered in such a way that the carbon atom carrying the OH group gets the smallest number. The position of substituents is then indicated by switchable numbers. The common and IUPAC naming of a few monohydric alcohols are given in this table below. You can see this table. There are almost 10 or 12 alcohols named here with their corresponding common names and IUPAC names. So now coming on towards the methods of formation. Alcohols can be easily prepared by the reduction of aldehydes, ketones, carboxylic acids, and their esters using a variety of reducing agents as discussed below. First one is the reduction of aldehydes and ketones. Aldehydes can be reduced to primary alcohols and ketones to secondary alcohols either by catalytic hydrogenation, that is addition of hydrogen in the presence of a catalyst such as nickel, platinum, palladium, ruthenium, or by the reduction with complex metal hydrides like sodium borohydride, lithium aluminium hydride, abbreviated as LAH. LAH reacts violently with water and therefore reductions with LAH are carried out in anhydrous diethyl ether or tetrahydrofuran, which is a nonpolar solvent. In contrast, NaBH4 reductions can be carried in water or alcoholic solution. When you see this reaction in which aldehyde is reacting with hydrogen in the presence of nickel or platinum or palladium or lithium aluminum hydride or NaBH4, it gives primary alcohol. When ketone reacts with the same reagents, it gives secondary alcohol. And when propanol reacts with these reagents, it gives propanol. When butanol react, it gives butanol respectively. Cyclohexane gives cyclohexanol respectively. What is the mechanism? Mechanism is reduction of aldehydes and ketones by lithium aluminum hydride or NaBH4 occurs by nucleophilic attack of hydride ion on the carbonyl group. All the 4 hydrogen atoms in LiH4 or NaBH4 may be successively used in reduction, and the alcohol is liberated from the intermediate metal oxides by hydrolysis. So when ketone react with LAH, it is reduced by hydrogen and it again reacts with ketone, which gives a structure name written here, which again react with another molecule of ketone, which gives trialdehyde and hydride. It again reacts with another molecule of ketone and gives the structure R2CHO4Al negative, which is again hydrolyzed by water to give secondary alcohol. Likewise, with the reduction with NaBH4, NaBH4 gives sodium plus borohydride ion, in which aldehyde is reduced again by hydrogen atom, and which subsequently reacts with 3 moles of aldehydes to finally give a primary alcohol. Reductions of alpha beta unsaturated aldehydes or ketones. Neither NaBH4 nor LiAlH4 reduces isolated carbon-carbon double bonds. However, in case of alpha beta unsaturated aldehydes and ketones, LAH usually reduces only the carbonyl group, leaving the double bond intact. However, with NaBH4, the situation is somewhat different. Since aldehydes are more reactive than ketones, therefore in case of alpha beta unsaturated aldehydes, the reduction of aldehyde group occurs preferentially. For example, when crotonaldehyde reacts with sodium borohydride and hydrolyzed by water, it gives crotyl alcohol. However, with ketones, a mixture of single reduction product, that is C double bond O reduction, and double bond reduction with both C double bond O and C double bond C reduction is formed, in which the product of single reduction usually predominates. You can see when cyclohexy-2-enol reacts, when cyclohexy-2-en-1-on react with LAH in dry ether followed by hydrolysis, it gives cyclohexene-2-enol in 98%. When this same compound, same substrate react with NaBH4 in the presence of alcohol, it gives 59% of hexene-2-enol and 41% of cyclohexanol. Since LAH has a relatively stronger tendency for reduction at the carbonyl group, therefore in the above case it gives 98% of cyclohexy-2-enol and 2% of cyclohexanol. In contrast, hydrogenation of C double bond C is much easier than that of C double bond O. Therefore, reduction of C double bond O can't occur without reducing C double bond C. In other words, catalytic hydrogenation reduces both the double bond and the carbonyl group simultaneously. You can see when crotonaldehyde react with hydrogen in the presence of nickel, it gives N-butyl alcohol. To prepare exclusively an unsaturated alcohol from an alpha-beta unsaturated aldehydes or ketone, a chemoselective reagent such as 9-BBN is used. 9-BBN stands for 9-bora-bicyclo-33.1 nonene and is obtained by the addition of B2H6, that is diborane, to 1,5-cyclooctadiene. To prepare exclusively, a chemoselective reagent is that which attacks one of the several different functional groups. Because of the bulky organic group attached to boron, 9-BBN adds to C double bond O much more readily than it adds to C double bond C. Thus, alpha-beta unsaturated ketone, when react with 9-BBN, it finally gives an alpha-beta unsaturated alcohol. Second reaction is Mirvin-Pondor-Verley reduction. It is commonly used for the reduction of ketones to secondary alcohols. The reaction is usually carried out by heating a ketone with aluminium isopropoxide in presence of isopropyl alcohol. During the reaction, ketone is reduced to a secondary alcohol at the expense of isopropyl alcohol, which is oxidized to acetone. To push the equilibrium in the forward direction, acetone is distilled off as soon as it is formed. This reaction is highly specific for aldehydes and ketones and doesn't reduce carbon-carbon double bonds. Therefore, it is a useful method of reduction of alpha-beta unsaturated aldehydes and ketones to alpha-beta unsaturated alcohols. Mechanism of this reaction is shown below. You can see this reaction in which aluminium propoxide transiting to structure written above will finally give secondary alcohol. Second reduction is reduction of carboxylic acids. Carboxylic acids can be reduced to primary alcohols by lithium aluminium hydride. Carboxylic acid, when reacting with lithium aluminium hydride in the presence of dry ether and hydrolysis, gives primary alcohol. When butyric acid reacts with same reagent, it gives butanol. Benzoic acid, when react with same reagent, gives benzyl alcohol. Because of the excellent yields it gives, LiAH4 is widely used in the laboratory. Since it is somewhat expensive, therefore, it can be used in industry only for the reduction of small amount of valuable raw materials to be used in the synthesis of certain drugs and hormones. Like aldehydes and ketones, the reduction of carboxylic acids by LiAH4 also occurs through nucleophilic attack by hydride ion. The initial product of reduction is an alkoxide ion from which the alcohol is liberated by hydrolysis. Carboxylic acids can also be reduced to primary alcohols with diborane. You can see this reaction. When carboxylic acid reacts with diborane, it gives trialkyl borane and it finally gives primary alcohols. Third reaction is reduction of esters. Esters can be reduced to alcohol by following methods. Bovolt-Blank reduction. This method involves the reduction of esters to alcohol with sodium in a refluxing alcohol. Actually, a mixture of two alcohol is obtained, one from acyl group and other from the alkoxy group. For example, acyl part, when reacting with sodium in the presence of ethanol, gives alkoxy part and R-OH. When ethyl butyrate reacts with sodium in the presence of ethanol, it gives N-butyl alcohol and ethyl alcohol. This reduction is believed to occur in several steps involving transfer of one electron at a time and the alcohol acting as a proton donor to the intermediate radical anion thus formed as shown below. You can see this reaction. Second reaction is with reduction with lithium aluminium hydride. Esters can be reduced with LiAH4 to give a mixture of two alcohols, one from the acyl part and the other one from the alkoxy part. Ethyl butyrate, when react with lithium aluminium hydride in the presence of dry ether, gives N-butyl alcohol and ethyl alcohol. The reduction occurs through initial nucleophilic attack of hydride ion on the carbonyl group with the expulsion of alkoxide ion to yield the aldehyde intermediate, which upon subsequent reduction yields primary alcohol. Then third is catalytic hydrogenation. On commercial scale, carboxylic esters are reduced to alcohols by catalytic hydrogenation in presence of copper chromite as catalyst under high temperature and pressure. Physical properties: physical state at ordinary temperature, lower alcohols are colorless liquids with distinct smell and burning taste. The higher members are colorless, odorless, waxy solids. Hydrogen bonding: since alcohols contain a hydrogen bonding attached to the strongly electronegative oxygen atom, therefore extensive intermolecular hydrogen bonding occurs among alcohol molecules. As a result, alcohols exist as associated molecules rather than discrete monomeric molecules as shown below. Boiling points: the boiling point of alcohols are much higher than hydrocarbons, alkyl halides, and ethers of comparable molecular masses. You can see the variation of boiling point. Ethyl alcohol has the highest boiling point in propane, which has then methyl chloride, when with dimethyl ether on the second position, methyl chloride in the third position, propane in the last position. The high boiling points of alcohols can be easily explained on the basis of intermolecular hydrogen bonding existing between their molecules. Quite a large amount of energy is needed to break these extensive hydrogen bonds, which hold a large number of alcohols molecules together. As a result, their boiling points are much higher than hydrocarbons, ethers, or alkyl halide of comparable molecular masses, which don't form hydrogen bonds. Amongst isomeric alcohols, the boiling points decrease with branching due to corresponding decrease in surface area. That is, boiling points decrease in the order primary, secondary, and tertiary. However, with increase in molecular mass, boiling points show a regular increase. You can see the boiling point of methyl alcohol is high as at the third point, while propanol at first point, ethyl alcohol at second point, and 1-butanol at the first point, propanol at the second point, butanol at the first point, propanol at the second point, ethyl alcohol at third point, and methyl alcohol at fourth point. Solubility: the lower alcohols are highly soluble in water, but the solubility decreases with increase in molecular mass of alcohol. The solubility of alcohols in water is due to the formation of hydrogen bonds between alcohol and water molecules. Extent of solubility of any alcohol in water depends upon the capability of its molecules to form hydrogen bonds with water. As the molecular mass increases, the hydrocarbon part, that is alkyl group, becomes larger, which resists the formation of hydrogen bond with water molecules, and hence the solubility goes on decreasing. In other words, the solubility of alcohols in water decreases with lengthening of carbon chain. For example, the solubility of N alcohols decreases as the length of carbon chain increases. कंपाउंड है N ब्यूटाइल अल्कोहल, जिसकी solubility सबसे ज़्यादा है, that is 8, N pentyl again उसके बाद, then N hexyl, and lastly N heptyl. Amongst isomeric alcohols, the solubility increases with branching. This is due to the reason that as branching increases, surface area of the non-polar hydrocarbon part decreases, and hence the solubility increases. For example, you can see isobutyl alcohol, secondary butyl alcohol has foremost solubility, then isobutyl, tertiary butyl alcohol has highest solubility, then secondary butyl alcohol, then isobutyl alcohol, and lastly the N-butyl alcohol. The hydroxyl part. Now coming on to the chemical reactions of alcohols. The hydroxyl group is the functional group of alcohols. Therefore, most of the characteristic reactions of alcohols are the reactions of OH group. In general, the chemical reactions of alcohol can be divided into the following three categories: reactions involving the cleavage of carbon-oxygen and hydrogen bond, that is ROH bond; reactions involving the cleavage of carbon-oxygen bond, that is ROH bond; and reactions involving both alkyl and hydroxyl group of alcohol molecule, that is reactions of alcohol molecule as a whole. The ease of cleavage of OH bond of alcohol follows the sequence: primary, then secondary, then tertiary alcohols. Reaction with active metals, that is acidic nature. Alcohols react with active metals like sodium, potassium, magnesium, and aluminium to form the corresponding metal oxides with the evolution of dihydrogen gas. When methanol reacts with sodium, it gives sodium methoxide. Ethanol reacts with magnesium, it gives magnesium methoxide. When tertiary butyl alcohol reacts with aluminum, it gives aluminum tertiary butoxide. This reaction suggests that alcohols are acidic in nature. The acidic character of alcohols is due to the reason that in alcohols, hydrogen is attached to the highly electronegative oxygen, which withdraws the electrons of OH bond towards itself. As a result, OH bond becomes weak and ultimately splits off as a proton. In other words, the acidic character of alcohols is due to the ability of oxygen atom to accommodate the negative charge. However, alcohols are weak acids, even weaker than water, is evident from the following reaction. When alkoxide ion react with a stronger acid, that is water, gives a weaker acid, that is alcohol. Here a stronger acid H2O displaces a weaker acid ROH from its salts, that is alkoxides. Reason: this is due to the reason that the electron releasing inductive effect of alkyl group increases the electron density around oxygen. As a result, the electrons of OH are not sufficiently attracted towards the oxygen atom, and hence the release of proton becomes difficult. In nutshell, we can see that the electron releasing inductive effect of alkyl group makes the alcohols weaker acids than water. Comparison of acidic character. As we move from primary through secondary to tertiary alcohols, the number of alkyl groups attached to the carbon having the OH group increases from 1 to 2 to 3. As a result, the electron releasing inductive effect would be maximum in tertiary alcohols and minimum in primary alcohols. In other words, primary alcohols are the strongest acids and tertiary the weakest. Thus, the acidic strength of alcohols follows the order primary, then secondary, and then tertiary. Obviously, the basic strength of the alkoxides follows the reverse order, that is, tertiary butoxide is the very basic, then primary, then secondary butoxide ion, and then primary butoxide ion. In presence of primary oxide ion, in presence of strong acids, alcohols also act as Bronsted bases. This is due to the reason that the presence of lone pair of electrons on the oxygen atom makes alcohols proton acceptors. When alcohol react with H2SO4, it gives oxonium ion and bisulfite ion. Alcohol being acidic react with Grignard reagents which act as strong bases to form alkanes. It may however be noted here that the alkane form corresponds to the alkyl group of the Grignard reagent. When alcohol reacts with alkyl magnesium halide, it gives alkane. When ethanol reacts with methyl magnesium iodide, it gives methane. When methanol reacts with ethyl magnesium bromide, it gives ethane. The hydrogen atoms attached to oxygen, nitrogen, sulfur are called active hydrogens. Compounds, alcohols, phenols, amines, thioalcohols, terminal alkyls containing active hydrogen on treatment with a Grignard reagent, usually methyl magnesium iodide, give quantitative yield of hydrocarbon corresponding to the alkyl group of Grignard reagent, that is methane. This procedure is called Zerivitnov's active hydrogen determination. Knowing the volume of CH4 evolved at NTP, the number of active hydrogens present in a compound can be determined. Thus, Zerivitnov's procedure is useful for determining the number of active hydrogens atom in a compound. Third reaction is reaction with carboxylic acids. Alcohols react with carboxylic acids in presence of a few drops of concentrated H2SO4 or dry HCl gas as a catalyst to form esters. For example, acid plus alcohol give an ester. When ethanoic acid reacts with ethanol, it gives ethyl ethanoate. This reaction, which is slow, is called an esterification. When HCl gas is used as a catalyst, the reaction is usually referred as Fischer-Spear esterification. The mechanism of esterification involves the initial protonation of carbonyl oxygen by the mineral acid to form the protonated carboxylic acid 1. As a result of protonation, the carbonyl carbon becomes more electropositive or electron deficient and hence readily undergoes nucleophilic attack by lone pair of electrons on the oxygen atom of alcohol to form tetrahedral intermediate. This intermediate then undergoes proton transfers to form another tetrahedral intermediate third. The intermediate third subsequently loses a molecule of water and a proton to give the esters as shown below. Isotopic tracer techniques have confirmed that esterification involves cleavage of OH bond of alcohols and carbon-oxygen hydrogen bond of acids as suggested by above mechanism. For example, when ordinary benzoic acid is esterified with CH3OH in which oxygen has 18, 18 oxygen radioactive, the ester methyl benzoate thus formed was found to be enriched in 18 oxygen, while the water formed contained only the ordinary oxygen. Relative reactivities of carboxylic acids and alcohols, the formation of tetrahedral intermediate second during esterification is confirmed by the observation that the rate of esterification is sensitive to steric hindrance as the number and size of substituents around the C double bond OH group or the OH group in alcohols increases, the rate of esterification slows down. Thus the order is acids का ये ऑर्डर रहेगा और alcohols का ये ऑर्डर रहेगा. आप देख लीजिए. Fourth is reaction with acid chlorides and anhydrides. When alcohols are treated with acids में मिथेनोइक acid सबसे ज़्यादा, then ethanoic acid, then propanoic acid, and then butanoic acid. Sorry, tertiary butanoic acid. Tertiary pentanoic acid. Alcohols में मिथेनॉल का ज़्यादा, then primary alcohol का, then secondary, then tertiary. When alcohols are treated with acid chlorides or anhydrides, the hydrogen atom of OH group is replaced by acyl group to form esters. Acid chloride alcohol के साथ react करेगा और क्या बना देगा? ester. This reaction is called acylation. If the acid halide and anhydride used are acetyl chloride and acetic anhydride, the reaction is usually termed as acetylation. However, if benzoyl chloride is used, the reaction is called benzoylation. Acetylation of alcohols is usually carried out in the presence of a base such as pyridine or dimethyl aniline. Acetyl chloride, when react with ethyl alcohol in the presence of pyridine, gives ethyl acetate, and acetic anhydride, when react with ethanol in the presence of pyridine, it gives ethyl acetate plus acetic acid. Benzoylation of alcohols is usually carried out in the presence of aqueous NaOH, since benzoyl chloride is not readily hydrolyzed by alkalis. NaOH की प्रेजेंस में ये रिएक्शन बेंजोइल क्लोराइड एंड इथाइल अल्कोहल की ये रिएक्शन गिव्स इथाइल बेंजोएट एंड HCl. P-nitrobenzoyl and 3,5-dinitrobenzoyl derivatives of alcohols are usually well-defined crystalline solids and hence are used to characterize alcohols. Reactions of alcohols with benzoyl chloride and its derivatives in the presence of aqueous NaOH is called Schotten-Bowman reaction. इसी को हम Schotten-Bowman reaction भी बोलते हैं. इसका mechanism you can see. Acylation of alcohols occurs by following mechanism, जिसके अंदर एसिड क्लोराइड मॉलिक्यूल जो होगा वो अल्कोहल के साथ में रिएक्ट करेगा और क्या बना देगा? एक स्ट्रक्चर बना देगा. उसके बाद दूसरा स्ट्रक्चर बनेगा और फिर फाइनली क्लोराइड आयन का अटैक होने से तीसरा स्ट्रक्चर बनेगा जो कि एक ईस्टर होगा. विद एसिड एनहाइड्राइड्स में जो स्ट्रक्चर है वो एसिड एनहाइड्राइड के ऊपर सबसे पहले अल्कोहल मॉलिक्यूल रिएक्ट करेगा. ऑक्सीजन अपनी लोन पेयर कार्बन को देगा और कार्बन अपनी लोन पेयर ऑक्सीजन को दे देगा. कार्बन अपनी बॉन्ड पेयर ऑक्सीजन को दे देगा. एक ऑक्सीजन नेगेटिवली चार्ज हो जाएगा तो दूसरा ऑक्सीजन पॉजिटिवली चार्ज ऑक्सीजन अगेन अपने अंदर से या अपने अंदर से हाइड्रोजन को निकाल देगा और क्या बना लेगा? ईस्टर. Reactions involving the cleavage of carbon-OH bond. Alcohols undergo a number of reactions in which cleavage of carbon-OH bond. In these reactions, order of reactivity of alcohols follows the sequence. Sequence क्या रहेगा? Tertiary, secondary, primary. Some typical reactions of alcohols involving the cleavage of carbon-oxygen bond are discussed below. जिसमें सबसे पहली है reaction with halogen acids. alcohols react with halogen acids to form haloalkanes, alkyl halides, and water. The order of reactivity of halogen acids is Hi, HBr, HCl. This is due to the reason that I negative is a better nucleophile than bromide, which in turn is better chloride ion. Order of reactivity of alcohols in these reactions is tertiary, secondary, primary. This order of reactivity can be easily explained on the basis of plus I of alkyl groups, which tend to stabilize the incipient carbocation or the carbocation intermediate. Since the stability of carbocations decreases in the order tertiary, secondary, primary, therefore the order of reactivity of alcohols also decreases in the same order, that is tertiary, secondary, primary. First reaction आती है with HCl. Due to low reactivity, the reactions of primary and secondary alcohols with HCl require the use of some Lewis acid catalyst such as anhydrous zinc chloride. However, no such catalyst is needed in the reactions of HCl with tertiary alcohols. When a primary alcohol reacts with anhydrous ZnCl2 or heating, so it gives chloroethane. When a secondary alcohol reacts with anhydrous ZnCl2, it gives 2-chloropropane. When a tertiary alcohol reacts with HCl but in the presence of room temperature, it gives 2-chloro-2-methylpropane. This reaction of primary and secondary alcohols with HCl in the presence of anhydrous ZnCl2 is called a Groves process. Now reaction with HBr. In this reaction also a small amount of concentrated H2SO4 is added as a catalyst. No catalyst is required for secondary and tertiary alcohols, which readily undergo dehydration in presence of concentrated H2SO4 to give alkenes. Ethanol when react with HBr, 48% gives bromoethane. With HI, alkyl iodides are formed. When methanol react with HI in the presence refluxing के साथ में तो आयोडोमीथेन बनता है. However, when an alcohol is treated with HI in the presence of red phosphorus, hydrocarbon is produced. Ethanol, when reacting with HI in the presence of red phosphorus, it gives methane and water and iodine. ध्यान से देख लीजिएगा अभी आप. Mechanism: primary alcohols react with halogen acids by SN2 mechanism, while secondary and tertiary alcohols tend to react by SN1 mechanism. से इसमें जो ये हेलोजन एसिड होगा ये क्या गिव करेगा, ये गिव करेगा H+ आयन और X नेगेटिव आयन. SN2 मैकेनिज्म से रिएक्शन चलती है. फर्स्ट रिएक्शन की अगर बात करूं तो SN2 मैकेनिज्म क्या होता है कि एक न्यूक्लियोफाइल अटैक करता है किसी इलेक्ट्रोफाइल के ऊपर. तो ये जो न्यूक्लियोफाइल है अल्कोहल ये अटैक करेगा हाइड्रोजन आयन, हाइड्रोनियम आयन के ऊपर और क्या बना देगा, प्रोटोनेटेड अल्कोहल. उसके बाद हेलाइड आयन का अटैक आएगा इस प्रोटोनेटेड अल्कोहल के ऊपर और क्या बना दिया जाएगा, ट्रांजिशन स्टेट स्ट्रक्चर ऑफ प्राइमरी अल्काइल हैलाइड अगेन. SN1 मैकेनिज्म में क्या होता है कि टर्शियरी अल्कोहल पहले आयोनाइज होता है और एक कार्बोकेटाइन फॉर्म करता है. वो कार्बोकेटाइन का जो अटैक होता है उस कार्बोकेटाइन के ऊपर न्यूक्लियोफाइल का अटैक आता है, टर्शियरी अल्काइल हैलाइड बनता है. Role of anhydrous ZnCl2 in Groves process. Anhydrous ZnCl2 being a Lewis acid accepts an electron pair from oxygen atom of alcohols. The presence of positive charge on the oxygen atom weakens the RO bond, which ultimately breaks to form a carbocation as shown in SN1. If the structure of R plus is such that it can undergo rearrangement to form a more stable carbocation, then the major product will be alkyl halide derived from the rearranged carbocation as discussed below. If, however, the concentration of zinc chloride is low, the reaction occurs by SN2. ZnCl2 plus HCl gives H plus ZnCl3 negative. Alcohol when react with hydronium ion, it gives structure. ZnCl2 negative Cl plus ROH2 plus SN2 रिएक्शन होगी और अल्काइल क्लोराइड बन जाएगा. रीअरेंजमेंट कैसे चलती है, रीअरेंजमेंट भी देख लीजिए. ये आप ध्यान से देख लो कि यहाँ पर रीअरेंजमेंट कैसे चलती है. Reactions of secondary and tertiary alcohols with halogen acids occur by SN1 and quite often gives rearranged products. For example, neopentyl alcohol on treatment with concentrated HCl yields 2-chloro-2-methylbutane instead of the expected neopentyl chloride. तो neopentyl alcohol का जो अटैक होगा वो हाइड्रोजन आयन के ऊपर आएगा, थोड़ा सा स्लो अटैक होगा और उसके बाद स्लोली वाटर मॉलिक्यूल निकल जाएगा। फिर क्या होगा, एक प्राइमरी कार्बोकेटाइन बनेगा, फिर वो एक लेस स्टेबल कार्बोकेटाइन होगा तो वो एक मोर स्टेबल कार्बोकेटाइन में जाने की कोशिश करेगा और ये कोशिश उसकी कामयाब भी हो जाएगी। थ्रू 1,2 मिथाइल शिफ्ट वो मोर स्टेबल कार्बोकेटाइन के अंदर पहुंच जाएगा। 2 क्लोरो 2 मिथाइल ब्यूटेन बाद में बना दिया जाएगा। सेकेंड रिएक्शन होती है रिएक्शन विद फॉस्फोरस हैलाइड्स। Reaction with phosphorus halides. Phosphorus halides such as PCl5, PCl3, PBr3 react with alcohols to form the corresponding haloalkanes और alkyl halides. जैसे अल्कोहल मॉलिक्यूल किसमें क्या रिएक्ट करेगा, PCl5 के साथ में और अल्काइल क्लोराइड और फॉस्फोरस ऑक्सीक्लोराइड बना देगा। ऐसे अल्कोहल फॉस्फोरस ट्राइक्लोराइड के साथ रिएक्ट करेगा और फॉस्फोरस एसिड बना देगा। मैकेनिज्म क्या होगा, the reaction between alcohol and phosphorus trihalide occurs by the following mechanism. It involves the nucleophilic attack by the alcohol molecule PCl3 when protonated alkyl dichlorosulfite 1 is formed. It subsequently undergoes nucleophilic attack by chloride ion forming the alkyl halide NHOPCl2. When alcohol molecule react with PCl3, क्लोराइड आयन निकल जाएगा और प्रोटोनेटेड एल्काइल डाइक्लोरोसल्फाइड फॉर्म हो जाएगा। प्रोटोनेटेड एल्काइल क्लोरोडाइसल्फाइड क्लोरोफॉस्फाइड जो बनेगा रिएक्ट विद अनदर मॉलिक्यूल ऑफ एल्कोहल अकॉर्डिंग टू स्टेप 1 and 2 to form RCl and HO dihydroxyl phosphorus chloride. Further reaction with dry hydroxy phosphorus chloride and alcohol according to steps 1 and 2 ultimately leads to the formation of 3 moles of alkyl halide and 1 mole of H3PO3 formed from 3 moles of alcohols and 1 mole of PCl3. The reaction between an alcohol and PCl5 occurs by a similar mechanism as shown below. PCl5 gives PCl4 plus and PCl6 negative. PCl6 negative react with RO plus H PCl4. It gives PCl5 and alkyl halide. Third है reaction with thionyl chloride. Alcohols react with thionyl chloride preferably in presence of a tertiary amine such as triethylamine or pyridine to form alkyl chlorides. Alcohol when react with thionyl chloride in the presence of pyridine alkyl chloride दे देगा, SO2 and HCl के escape off हो जाएंगे। इथाइल अल्कोहल SOCl2 के साथ में रिएक्ट करके pyridine के साथ में और इथाइल क्लोराइड दे देगा, फिर SO2 और HCl escape off हो जाएंगे। This reaction is called Darzin's procedure. Since SO2 and HCl both being gases escape into the atmosphere, leaving behind almost pure alkyl halide, therefore SOCl2 method is preferred over phosphorus halide method for the conversion of alcohols into alkyl chloride. Mechanism कैसे होगा? The nucleophilic attack of the alcohol molecule on thionyl chloride gives an adduct which subsequently loses a proton and a chloride ion to form alkyl chlorosulfide. This then undergoes another nucleophilic attack by chloride ion forming an alkyl chloride SO2 and chloride ion. Role of a base. Base क्या करेगा? Pyridine catalyzes this reaction in the following two ways. First is it neutralizes HCl produced in the first step, favoring the formation of alkyl chlorosulfide. Second, it helps to pull out chloride ion from alkyl chlorosulfide, thus formed, thereby favoring the formation of products. Reactions involving both alkyl and hydroxyl groups. First reaction आती है dehydration of alcohols. Alcohols की dehydration. By dehydration we mean removal of a molecule of water. Alcohols on dehydration gives alkenes. The dehydration is carried out by heating a suitable alcohol with protonic acid such as conc H2SO4 or H3PO4 These acids such as anhydrous zinc chloride or alumina can also be used. Alcohol in the presence of an acid gives alkene. Actual temperature and the strength of acid, however, depends upon the nature of alcohol used. For example, primary alcohols such as ethyl alcohol and propyl alcohol undergo dehydration when heated with 95% sulfuric acid at 443 to 453 to give ethylene and propylene respectively. On the other hand, dehydration of secondary and tertiary alcohols occur with dilute H2SO4 and at lower temperatures. Dehydration of secondary and tertiary alcohols occur with dilute H2SO4 and at lower temperatures. For example, सेकेंडरी अल्कोहल के साथ जब 60% सल्फ्यूरिक एसिड रिएक्ट करेगा तब प्रोपाइलिन बना देगा. टर्शियरी अल्कोहल के साथ जब 20% सल्फ्यूरिक एसिड रिएक्ट करेगा तो आइसोब्यूटाइलिन बना दिया जाएगा. Order of dehydration of alcohols follow the sequence: tertiary, then secondary, then primary. In industry, the dehydration of alcohols is carried out by passing the vapors of an alcohol over heated alumina at 623 से 633 Kelvin. Reactions of alcohols under different conditions. एक तरह से रिएक्शंस चलती हैं इसकी अल्कोहल्स की डिफरेंट कंडीशंस के अंदर. तो वो कैसे होती हैं? इथाइल अल्कोहल होगा. इथाइल अल्कोहल किसके साथ में रिएक्ट करेगा? H2SO4 के साथ में इथाइल हाइड्रोजन सल्फेट बना देगा. फिर उसके बाद डिस्टिलेशन से रिड्यूस प्रेशर में तो ये क्या बना देगा? डाईइथाइल सल्फेट. सेकेंड, अगर इसको एक्सेस ऑफ इथेनॉल से ट्रीट किया जाए तो जो ये डाईइथाइल सल्फेट बना है, डाईइथाइल सल्फेट, यही डाईइथाइल सल्फेट क्या बना देगा? डाईइथाइल ईथर बना देगा. सॉरी, व्हेन हीटेड विद एक्सेस ऑफ इथाइल अल्कोहल, ये एक्चुअली जो डाई हाइड्रोजन सल्फेट बना है ना, ये अगर इसको हम फिर से इथाइल अल्कोहल के साथ ट्रीट करें तो ये डाईइथाइल ईथर बना देगा और H2SO4 बना देगा. अगर इसी को अगर हम H2SO4 एक्सेस में हीट करें तो ये इथिलीन बना देगा. इसका मैकेनिज्म आप देख सकते हैं यहाँ पर. मैकेनिज्म यू कैन सी हियर. जिसमें सबसे पहले क्या होगा? अल्कोहल मॉलिक्यूल, सॉरी अल्काइल हाइड्रोजन सल्फेट, उसका कंसनट्रेटेड H2SO4 से रिएक्ट कराने पे इथिलीन मिलेगा और साथ में H2SO4 मिलेगा. स्टेप 1 के अंदर इथेनॉल जो है वो हाइड्रोजन से रिएक्ट करके प्रोटोनेटेड अल्कोहल ऑक्सोनियम सॉल्ट बनाएगा. स्टेप 2 के अंदर ऑक्सीजन के ऊपर क्योंकि एक पॉजिटिव चार्ज आ चुका है तो रिएक्शन थोड़ी सी स्लो होगी और यहाँ से वाटर मॉलिक्यूल का एलिमिनेशन होगा. तो ये स्टेप से स्लो और ये रेट डिटरमाइनिंग स्टेप होगी रिएक्शन की. किसी भी रिएक्शन की स्लो स्टेप उसकी रेट डिटरमाइनिंग स्टेप ही होती है. It may be noted here that dissociation of oxonium salt requires energy, which is supplied by the energy released during solvation of carbocation by ion dipole interaction. Dissociation of oxonium salt requires energy. उसको energy require होती है, which is supplied by the energy released during the solvation of carbocation by ion dipole interaction. ion dipole की तरह से वो कार्बोकेटाइन solubilize हो जाएगा, तो उस वजह से जो एनर्जी रिलीज होगी वो एनर्जी रिलीज होगी, उसी एनर्जी का यूज़ किया जाएगा उस प्रोसेस को करवाने में. स्टेप थर्ड जो है वो एक फास्ट स्टेप है. जो ये कार्बोकेटाइन बना है, ये कार्बोकेटाइन अपने में से एक हाइड्रोजन आयन को निकाल देगा और फाइनली इथीन बन जाएगा. द होल प्रोसेस रिवर्सिबल है. इन ऑर्डर टू शिफ्ट इक्विलिब्रियम टुवर्ड्स राइट, strong acids and high temperatures are used. When the resulting alkene being more volatile than the starting alcohol escapes from the reaction mixture. इसके सपोर्ट में कुछ एविडेंसेस भी दिए गए हैं. इसके सपोर्ट में बहुत सारे एविडेंसेस दिए गए हैं. तो एक एविडेंस अगर मैं बात करूं तो ये है कि रिलेटिव ईज ऑफ डिहाइड्रेशन. Step 2 in the above mechanism involving the formation of carbocation is the redetermining step of the reaction. Evidently, greater the stability of carbocation, more easily it will be formed and hence more readily alcohol will dehydrate. Now, since the order of stability of carbocations follows the sequence tertiary, secondary, then primary, hence the ease of dehydration also follows the same sequence, that is tertiary, secondary, and primary alcohols. This was all about this chapter. Thank you so much. Thank you so much.